here are some of the simulations that I actually ran for these. Let's see, this one I chose only to show one trial because it was just varying the birth rate of the population, and we actually had similar outcomes for both of these. And as you increase the birth rate, it's going to go, the population is going to go to infinity faster. That's sort of logical. And also you can see different sample paths every time, like what we talked about. Okay. The single species birth and death. In these two, I just designated that the death rate is going to be greater than the birth rate. So it makes sense that you're going to see a decrease here, a decrease here. But this is a very smooth path because before it is even computed, it subtracts the birth and the death rate. Over here, it treats each of them individually, so that's why you get the staggering. That's why we use the stair-step line to better represent that. Trial 3 may seem kind of trivial when you look at this. If you have exactly the same birth rate and exactly the same death rate, you're going to get a straight line. However, the stochastic model shows us that that's not always true. There is going to be some fluctuation in there because there's always the chance that not the same thing happens every time. But if you sort of look at the average, it does average around 5, which is in agreement with the deterministic case. Predator-prey simulations. Let's see. For the one on the top, I just sort of chose generic values to generate this so we can sort of get an idea of what to expect with a predator-prey system. In this case, the birth rate of the predator was less than the death rate of the prey. So you can see the predator actually averages out to around 50, the prey averages out to around 100, and we actually see the agreement here. Like if you look at the heaviest, the densest part of this, it's going to be about 100 for the prey, about 50 for the predator. Trial 4, I was trying to find what would happen if I knew that at least one of the populations, one of the species was going to go extinct. And this is where actually I put both of the birth rates and both of the death rates of both species to be exactly the same. Right from the start, we get a decrease in the prey population. As soon as it hits 0, the predator population drops off 2. And over here, we get pretty much the same thing. It immediately starts off decreasing, decreasing, decreasing. And the way that the stochastic is actually designed is that as soon as one species or the other hits 0 in size, or if the desired time span runs out, then it will stop the process. So in these 3 cases, the prey population hit 0, and given our knowledge of the model and what would happen given our assumptions, we know that immediately following the predator population will also go to 0. The carrying capacity, if you look at both of these two, if you take this one and squash it down to about that size, you're going to have about the same shape. Even though these do have 3 different sample paths, you will get about the same shape with that. This bottom graph here indicates that the carrying capacity of the habitat for the prey just was not enough, did not have enough available so that the prey population or predator population could actually sustain itself. So that's why it ended up dying off here. But one thing I would like to know, even though we know the predator population goes to extinction before 10, still seeing this little bit of wavering here later on makes us wonder, if there is something that is given the particular solver that we chose, if there could have been something better chosen for it, because everybody knows once you get to a 0 population, there's no way it can come back from the dead. So it's just going to stay dead. So that was something that made us question the use of, or made me question the use of the deterministic model in this case, is that there, even though we know it goes to 0, there really should not be that wavering there. So there is always room for improvement on that. Okay, this one, I thought this was extremely interesting. As you can see, here the predator population goes to 0. Here the prey population goes to 0. Here the prey population goes to 0. All three of these trials, one population or the other went extinct. Over here, they're well above 0. I found that very strange that perhaps, in this case, the stochastic model was picking up on something that the deterministic model missed entirely. The simulations for the refuge, we know we're guaranteed at least a minimum number of prey every single time, so we know that there are always going to be some predator individuals around as well. Let's see, for the one on the top, let's see, the initial conditions. All right, I designated the death rate of the prey was higher than the birth rate of the predator, and the refuge, actually, the refuge size in all three cases is the same. So as you can see from the deterministic model, predator averages out to around 75. The prey population averages around 150. We see agreement over here in this one. You look at the bulk in both predator and prey sides, and you will see the agreement there. Okay, in this case, actually I increased the predator birth rate, so it was more than the prey death rate. That's why we see the switch here, that the predator population is going to be greater than the prey population. And in the last one, actually I set the death rate of the prey and the birth rate of the predator exactly the same, and there's very little fluctuation at all, and they both come out around the same. You can see this is true here, about 75, and just a little above, around 80 here. So they actually sort of mimic each other. They're very close. Okay. Overall, in this study, it was clear that the stochastic did not suffer the noise problem, as we had seen with that one trial where we knew the population of the prey predator went extinct, but we still saw that wavering after time. And I had looked on the website of the people who actually created MATLAB, and they admitted that there are noise problems, and of course my experience in numerical analysis classes, there are noise problems with certain solvers and certain techniques. And if perhaps I had had extra time to devise a specific numerical solver for the differential equations of the deterministic model, I might have been able to reduce that noise so it didn't have as much effect. Let's see, generally speaking, the deterministic model is better for determining how long it takes to reach stability or otherwise. And that was pretty obvious, actually, from looking at the graphs between the deterministic and the stochastic. Deterministic, you can sort of tell about how long it's going to take for something to happen for you to reach the end result. But with the stochastic, you've got so much overlapping and everything, you can't really tell exactly how long it's going to take. Plus, every sample path is different, so it is more useful if you're looking for what is actually occurring during all of the movement instead of just the end result. In most cases, the paths are the same between the two models. The only exception, the biggest exception, was the one that showed extinction of one population or the other all the time, whereas the deterministic counterpart to it actually indicated a leveling off. So that was one exception. The only exception I actually found was with that particular model. Stochastic modeling treats each probability independent of the others. That's like if you go back to the simple birth-death models, in the deterministic case, the birth and death rates are subtracted before it's even solved. But in the stochastic model, everything is given pretty much a fair chance of occurrence. And so I sort of liked that. Steady state analysis, and this is speaking more generally, is more difficult, however, for the stochastic models. In deterministic models, the hardest part about them is getting all of your units to match and dimensional analysis to try and combine as many terms as possible, as many extra variables as possible. But, and really it's very simple and easy to do by hand for 1 or 2 species. Of course, as you get more species, it is going to get more complicated. But even for the basic stochastic models, even for the very simple ones that you're looking at only 1 species, a steady state analysis actually is referred to as the stationary probability distribution, which you can find it if you know the initial distribution of the system, but in most cases we don't. So that is why we use it more. We use stochastic modeling more for the mean and the variance instead of trying to figure out where the entire system is going to go, because that steady state analysis is very difficult because you have to show convergence in distribution from the initial distribution to the stationary probability distribution. In conclusion, both models are useful in their own ways. If you want to see how long it takes for some result to happen, deterministic model is great for that. If you want to know what happened along the way, stochastic modeling is better for that. There are various ways to enhance results, as I sort of discussed as I was going through this. One of them might include specialized numerical scripts to get higher accuracy. Another one might be comparing the deterministic equations to the stochastic differential equations. The main reason why I chose not to do that is because seeing the limitations on the deterministic differential equations with the noise problem, I didn't want to have that same problem with the stochastic thing. I wanted to have at least one of them free and clear of that type of problem to see really what they could do. And also varying the components of the stochastic model. Because there are many different ways that you can add numbers together to get 6, you know, the same thing applies here with the stochastic model. We could have tried any of those variations to see really how they would compare with the deterministic counterparts. I think, and there are the references that I used a little bit. So if you think everybody in the math department, which only 1 person is here, so that's okay. And,
I got yelled at for letting you guys do it in the morning.
That's okay. So that's all I have. Any questions? Okay, am I done?
What did you repeat for Shannon and Ashley's benefit who failed? What was that? What did you learn? What was the biggest thing you learned from this experience? So that way you have to answer my questions since Tammy had to answer questions.
Okay. The biggest thing I actually learned from this experience is how to take a textbook and actually learn a technique. Actually learn something just by reading a textbook. So I didn't think it was actually possible before. A lot of times I hate to do this, but math books put me to sleep reading them. So, but this one actually, as I got to the point where I felt like I was learning more and understanding more, it became really interesting. And even now I have a hard time putting it away and saying, no, you're done, no more. But I think that was probably the biggest experience, is just learning how to learn on my own.
Do you think you can sell yourself that way to an employer? I can learn just about anything? I was thinking about where you were defending.
You need one of those Eat at Joe's signs, you know.
You said that, now you have to figure out how you have to you market yourself that way.